Today is session 2 of Rise of the Drones. We concerned ourselves last week with drone platforms that were remotely controlled and the policies of targeted killing that have developed as a consequence or alongside them. But today we are discussing or considering the question of the emergence of robotic systems that are able to operate autonomously in the context of war, and the increasing uses of artificial intelligence more generally in the military context. So again, last week we were thinking about systems that were remotely controlled that still remained essentially under human guidance. Now we are going to look at the growing importance of systems that are able to act independently of human input, including in the areas of the selection of targets and the very decision to use deadly force. A term has come to the fore in the last 10 years or so, which is that of lethal autonomous weapon systems, or LAWS. And there's been considerable debate about the emergence of these systems, about their future development, about the various challenges and problems that they pose. For some, we are on the cusp of a robotic revolution in military affairs, as momentous, if not more so, than the introduction of gunpowder, levée en masse, and nuclear weapons. And indeed, what we'll do in the following session is consider what the widespread deployment of autonomous systems might mean for the future of war, of our societies, and of humanity itself. Now, to begin with, we need to clarify some of our terms here. There's some important definitional considerations and some pretty thorny issues about how you conceptualize ideas such as autonomy and how you interpret the differences between specific systems. A first thing to underline is an important difference between automation and autonomy. With automation, we are referring to the ability of a machine to perform a task automatically in applying predetermined responses to a set of possible environments or inputs. Now, the history of automation is a very old one. Any mechanical system which has some potential variation in its behavior, or even that is capable of reproducing a task repeatedly, can be thought of as automated. Clockwork mechanisms are automated. Various industrial machines, of course, also fall under the category of automation. And many technological systems include components that are automated. Autonomy, on the other hand, implies a capacity for a system to operate within an uncertain environment, with the notion that the system is able to adapt or learn. So instead of having all the types of behaviors predetermined within the system will itself be able to devise unforeseen responses to unforeseen circumstances. Now, these distinctions are not always straightforward to make in concrete systems, and they are subject to considerable debate. Where we draw the line between automation and autonomy is not necessarily very clear-cut. In particular, it gets very thorny when we think about the question of intelligence. So when can a system be considered intelligent? Well, one might say that autonomy, which is something we think of as a characteristic that human beings possess, can be a manifestation of intelligence. But the definition of intelligence is also a difficult one to operationalize. For instance, one might see automation as simply the unthinking, inflexible application of rules. But in fact, when we look at more sophisticated, so-called autonomous would-be intelligent systems, these also typically rest on the application of rules. For instance, or in this instance, algorithms in particular. And so the question here becomes, well, it's not so much that you have systems that are based on rules and systems that are not based on rules, but it seems perhaps that beyond a certain complexity in the rules, then we might have certain types of new forms of behavior that might emerge from a system. Again, where you draw that line is difficult to determine. Where that automation, or where that emergence of intelligence appears and how we necessarily recognize it is also difficult. When we're used to thinking of human intelligence as the exercise of some form of autonomous agency, the idea that we decide to take this or that action, that we have a free choice in determining courses of action. But of course, one could also consider that human decisions, human behavior, are ultimately governed by an accumulation of unconscious rule-based processes realized in the firing of millions of neurons, which goes on continuously as we take decisions or as we act in the world. This opens up, of course, very thorny issues about the existence of free will and of agency, whether we are determined ultimately by sets of physical processes and our sense of agency is effectively fictitious, or further difficult philosophical issues about how we go from matter, organic matter, the brain and its connections, and we somehow have this qualitative leap to what we experience as consciousness. Is this consciousness merely a natural emergence from this material basis? And if so, then would we expect machines at a certain level of complexity in their cognitive processes to effectively attain some sense of consciousness? Thorny, difficult questions. Undoubtedly, we cannot resolve all of them here, but it is important to think about what we mean by autonomy and what we mean by intelligence when we talk about these systems, because that obviously has a major bearing on some of the other issues that we're going to discuss today. In passing, I think it's worth noting the affinity that military organization has with rule-based behavior in the first place. We've looked at the important role of drill instructions, tactical training in the preparation for war. All of these are designed so that soldiers can be expected to respond in a desired fashion when they encounter expected situations in war. So war is an activity that is carried on within very chaotic circumstances, and discipline, organization, rules have been an integral part of the way in which military organizations have dealt with this kind of problem. And so we can see an affinity here between the kind of military mindset and its rule-based form of organization and what certain technical systems, and notably computing systems, can provide in terms of their own rule-governed, explicitly rule-governed behavior. Now, a second set of distinctions that is important for us to consider here when discussing different military systems is their relationship to human operators. And that has become an increasingly relevant question as the possibility of fully autonomous systems has come to the fore. So there was a distinction then drawn between being in the loop, on the loop, and off the loop. In the loop refers to when humans are needed to authorize the use of force. So we might have a system, a machine that identifies a target automatically, but in order to fire, in order to deliver force, it has to require the human to approve the targeting process. So the human remains in the operating loop. A second category is on the loop. On the loop is where the machine performs autonomously. For instance, it selects targets, it engages targets independently, but it allows a human operator to supervise this process continuously, and the operator can choose to override actions at any moment. So if the system decides to selects a target, is about to engage it, the operator is able to abort that operation if they so choose. So this has often been seen as a form of human oversight to ensure that autonomous systems don't act in ways that we would not want them to. There's questions, and we'll touch on those again later, but there are questions, of course, about how realistic such on-the-loop designs can be when systems start operating at high degrees of complexity and speed, in which the operator may have a theoretical ability to stop the system from operating, but in fact will generally not be in a position to do so in an informed fashion. Finally, we have off-the-loop, an off-the-loop category where the system can operate independently, and so there is no completely independently, and so there is no human input or control over the machine after it has been originally designed or deployed. This is usually the fullest sense of autonomy. But note already here that these categories of in the loop, on the loop, and off the loop don't necessarily map so neatly with the other distinctions we've made regarding automation and autonomy, with the assumption, for instance, that autonomous systems are more sophisticated, more intelligent. Well, an example of an off-the-loop weapon system would be a landmine. Once you lay a landmine, put it in the ground, this mine stays in the ground and awaits some form of stimulus, a vibration or sound or something it's been effectively programmed to respond to, and then it detonates. Now, that system therefore has no human input. It is entirely off the loop, but it is, by most intents and purposes, a pretty dumb weapon. It has no sophisticated ability to learn. It has only one mechanism, which is to perceive a particular input and to trigger its explosive mechanism. So it's not so simple as to assume that as we move from in the loop to off the loop, we're dealing with more sophisticated machines. We might well be in the context of autonomous systems, that may be the case. But we can also have pretty simple, dumb devices that can be considered to be off the loop, and pretty sophisticated ones that can be involved in the loop, that might rely on the continuous feedback between human and machine. Now, as we've seen before, modern militaries have, of course, embraced and led technological development for a long time. They've seen technological breakthroughs, technological preeminence as central to their activity and to their prospects of dominating future wars. And so presently we are seeing considerable resources and extensive doctrinal thinking being dedicated to robotic warfare. As the Deputy Defense Secretary Robert Walk put it in 2015, I'm telling you right now, 10 years from now, if the first person through a breach isn't a freaking robot, shame on us. And so the US has been pursuing for the last decade or so what it's now calling its third offset strategy. This is a response to what were described previously as a first and a second offset. So these were strategies devised to balance the main US adversary. Of course, in the first and second offsets, this was essentially the Soviet Union. So in the first offset, the United States tried to balance or to counterbalance the Soviet superiority in conventional military forces, at least in the European theatre, through a nuclear advantage. In the 1970s and 80s, it pursued precision strike, that's to say the use of precision weaponries, better communications, greater use of computers and so forth, what has often been referred to as the revolution in military affairs. And it did so, again, as a means to attain military preeminence. The third offset that we are allegedly in the midst of is a strategy centered around autonomy and artificial intelligence, a further development of guided munitions, the development of cyber warfare and electronic warfare. As the same Robert Walk puts it, the third offset is simple. At the core, AI and autonomy will lead to a new era of human-machine collaboration. So we're in the midst of a major push within the United States to develop robotics and artificial intelligence. This third offset is related to what is also being called in economic circles the fourth industrial revolution. So there is an idea that there's a set of technologies that are revolutionizing production and in which significant leadership will yield major benefits. Again, similar technologies are being spoken about: autonomous robots, simulation, the Internet of Things, augmented reality, big data, and so forth. Now, this fourth industrial revolution is assumed to have come in the aftermath of three previous ones. A first one led by the innovations of steam and water, the steam age if you want. A second centered around technologies of electricity. The third of information technology. Now, what each of these industrial revolutions did was to displace certain activities of human labor, mostly initially through processes of automation and now increasingly through processes of autonomy. And you can see how this is shifting the kinds of human labor that it is assisting or displacing. So in the first three revolutions, it was primarily physical labor that was being replaced. So the whole industrial age, of course, in the development of factories, involved machines producing what previously humans would be, such that today the average factory contains relatively little physical labor. However, the fourth industrial revolution is thought to displace also vast amounts of human cognitive labor, and so that it's in the realm of cognition that actually most of the technological breakthroughs are being made, and that areas in which human activity was remained preeminent may soon be replaced by machines. And there is considerable discussion in economic circles about the implications of this, about whether this will cause significant structural unemployment, whether entire professions, the legal professions, the medical professions, various kind of managerial professions, whether all of these will effectively, in large part, be displaced by artificial intelligence within the next couple of decades or so. Now, the whole idea of artificial intelligence, of course, is not new in itself. It's really it appeared really at the same time as the first computing technologies in the 1940s and 50s, and great hope was placed in these early periods in the development of artificial intelligence. In the 1950s, there were vast programs to develop artificial intelligence. A lot of military funding went into this already at the time. The military saw great potential in artificial intelligence, and some very bold predictions were made about how fast artificial intelligence would develop. In fact, it disappointed on most fronts, so much so that in the post 1980s, there was something called like an AI winter, a period of disappointment in the breakthroughs that never came, and as a result, decreases in funding and so forth. We are, however, in a new age of AI today, with a number of breakthroughs in artificial intelligence through the applications of, if not new techniques, at least techniques that have benefited from the increase in computing speed available to them. So techniques such as deep learning, neural networks, big data analytics, the ability to treat very large amounts of data and to use this data as a way to train artificial intelligence has yielded significant results in a wide range of areas, and there is hope that this will now be able to tackle problems that had previously found to be impossible to process with previous artificial intelligence approaches. Now, the holy grail within artificial intelligence is what is called AGI, or artificial general intelligence. Now, this is another concept that is not very specifically defined, because it again revolves around the question of what intelligence actually is, but generally speaking it refers to a level in the development of AI in which artificial intelligence would either equal or surpass human intelligence in all tasks. That's to say, a general intelligence that would be able to solve a variety of problems rather than very narrow, specific, circumscribed problems. Now, AGI remains still quite remote here at this point in time, but AI is already increasingly outperforming humans at specific tasks. In the last few years, the high-profile performance of the AlphaGo software has been much remarked upon. Chess obviously had already been mastered by computing systems in the 1990s. A famous chess game with Garry Kasparov in which the IBM Deep Blue system demonstrated its superiority. But the mechanisms or the processes, the kinds of techniques used to defeat humans at chess were simply not able to process Go because of this East Asian game. Involves far too many permutations to use the kind of brute strength approaches that were being used at the time. So it is through deep learning and through big data analytics, ultimately, that AlphaGo has now been able to best even the most superior human Go players, and that has been a quite spectacular demonstration of these new approaches and what capabilities they may have. In August 2020, the US military organized what it called the Alpha Dogfight Trials, in which AI agents took on human pilots in simulated aerial combat. And in the final event in August, the artificial intelligence won the event 5-0, showing again another kind of advance in artificial intelligence and its ability to outmaneuver the best human pilots. And so obviously giving some sense of a future in which aircraft may no longer be piloted by humans, but by AI. But there's also new forms of distributed intelligence that are being experimented with. So we shouldn't only think of artificial intelligence as the development of systems that on their own seem to replicate some form of human intelligence through a kind of central processing system. But there are also attempts to work with very vast numbers of fairly straightforward, simple systems whose intelligence emerges through the interaction of their parts. This is the model known as the swarm. And the inspiration for the swarm is often the behavior of social animals such as ants and termites and bird flocks and so forth, which of course is a form of intelligence that doesn't rest on complicated processing systems individually. A single ant or a single bird is not, of course, a highly intelligent creature. However, together, the multiplicity of their interactions can lead to very adaptable, very dynamic behaviors. And so some military thinkers have imagined plans for millions, maybe even billions of very cheap micro robots interacting together as a swarm. These low-cost, uninhabited systems could be built in very large numbers, could flood a zone in the context of a battle, overwhelming enemy defenses by their sheer numbers. So rather than having very expensive, exquisite, complex robots, if you want, one could imagine very cheap, very nimble, very replaceable systems, but which together would combine to be very effective and very difficult to neutralize. There's a kind of back and forth here, of course, between these ideas that we've discussed briefly in the industrial sector and the economic sector and what's going on in the military. The US military in particular has been drawing inspiration for a long time on what it's seen evolving in the civilian sector, where, of course, today, very differently from in the past, where AI was often largely military funded, today a lot of AI, a lot of big data analytics, much of the cutting edge is happening within civilian companies, and so it is civilian companies that are being brought in by the military to do some of its work. And so ideas such as the Internet of Things, the idea that we will be surrounded by millions, if not billions, of common objects that will all have their own IP addresses, that will be connected to one another, that will have what's called pervasive computing, where your fridge is processing as much as your computer and your wristwatch. This idea has been given a military spin with the idea of the Internet of Battle Things, again, which relates back to this question of the swarm, the idea that collective forms of intelligence don't necessarily have to do with or can be an emergent form of intelligence that is greater than the sum of its parts. So according to the advocates of the Internet of Battle Things, we have here a vision of pervasive computing, communication and sensing, where everything will be a sensor and potentially a processor, and also perhaps potentially a weapon. This, of course, also suggests the idea of a world in which any system is liable to be weaponized, to be any system that's on the network, on the internet, could be brought into the processing mesh of the military, become a component within a war. Now, algorithms are also being used to process vast quantities of data to enhance human decision making. So AI is not only embedded in specific weapon systems, but it also is becoming a very important aspect of intelligence gathering and feeding the flows of information that are needed for the conduct of war or strategy. Here again, there's an interesting dance between private and public actors. One high-profile case is that of Project Maven. It was revealed in 2018 that Google had been contracted by the Department of Defense to apply machine learning and computer vision to the analysis of large quantities of drone footage. This prompted protests by Google staff, and eventually the company pulled out, did not renew its contract with the Department of Defense as a result of this. The project itself, however, survived, remains in development, and was picked up by a company called Palantir, which is a data analytics company, has many defense and intelligence contracts, company led by Peter Thiel, the founder of PayPal and a Facebook board member. So this alliance of military and civilian or big tech companies is a very important dimension of this. And again, the kind of big data techniques that have been experimented with in the industrial sector are being also applied in the military sphere. And this proximity of investors in social media and other technology and the military is something that we should be quite attentive to. So we can speak in a sense of robot war, but also of algorithmic war, all of which imply war increasingly being thought of as data, and as data that is being processed somewhat by humans, but also in increasing part by machines, and within wider systems in which humans and machines are largely integrated, but also where machines increasingly acquire some autonomous powers of decision. And so we'll now look at some of the possible consequences, implications, and problems that this poses for the future of war.